Have you ever really thought about the physics that keeps a satellite locked in orbit? Or what glues you to your seat in a roller coaster loop? It's all about the science of spin, or what physicists call uniform circular motion. And it turns out we can pretty much break it all down with just three core equations. Okay, I want you to think back to the last time you were on a merry-go-round, or maybe one of those wild spinning rides at a carnival. You know that feeling, right? That powerful sensation of being thrown outwards. But what if I told you that feeling is kind of an illusion? That the real physics is actually pulling you in. To get why that is, we've got to get our terms straight. So, yeah, before we can crack that mystery of being pulled inward, we need to agree on what we're even talking about. Let's start with the official name for this kind of motion. Okay, so the fancy term is uniform circular motion. Now, that word uniform is super, super important here. It means the object is moving at a constant speed. It's covering the same amount of ground around that circle every single second. But, and this is the part that trips everyone up, its velocity is not constant. And that one tiny difference, it changes everything. This brings up a huge question, one that honestly feels like a total paradox. How can something be accelerating if its speed never changes? I mean, it sounds impossible, doesn't it? In our day-to-day lives, acceleration is hitting the gas pedal or slamming on the brakes. So if your speedometer is locked in place, where on earth is the acceleration coming from? Well, the whole secret is hiding in the difference between two words we use all the time. And here is the key. In physics, velocity is a vector. That just means it has two parts to it. It's got a magnitude, that's the speed, and it's got a direction. So to change your velocity, you can either change your speed, or change your direction, or do both. So let's go back to moving in a circle. Even if your speed is perfectly constant, think about it. Your direction of travel is changing at every single instant. You're constantly turning. And since your direction is changing, your velocity has to be changing. And here it is, the big reveal. By definition, any change in velocity is acceleration. So, moving in a circle is always a state of acceleration. This special kind of acceleration has a name. It's called centripetal acceleration. Centripetal literally means center-seeking. It's not pushing you out. It's the inward-pointing acceleration that's constantly yanking you from your straight path and forcing you to stay in that circle. And we can actually calculate this with our very first core equation. It says that centripetal acceleration, AC, is equal to your speed, v, squared, divided by the radius of the circle, r. Now just think about what that means for a second. The faster you go, or the tighter that turn is, the way more acceleration is needed to keep you on that circular path. But you know, talking about speed in meters per second, what we call linear speed, it's not always the easiest way to describe things that rotate. Sometimes it's just way simpler to talk about how fast something is spinning, and that gives us a whole new angle on speed. This is what we call angular velocity, and we use the Greek letter omega for it. Now, don't get thrown by the units radians per second. Just think of radians as another way to measure angles, kind of like degrees. Honestly, the best way to picture it is like the RPMs on your car's dashboard. It's not about how fast you're going, it's purely about how fast you're spinning. So let's put them head to head. Linear velocity, v, that's your path speed, what your speedometer would read. Angular velocity, omega, that's your turning speed. One tells you how fast you're moving along the curved line, the other tells you how fast you're sweeping around the center point. Two different ways to look at the same motion. And this new way of thinking gives us a second really powerful way to find that exact same centripetal acceleration. With this one, AC is just the angular velocity, omega, squared, times the radius. This is the perfect tool for when you know how fast something is spinning, but maybe you don't know its exact path speed. Okay, so we have these two different ways of looking at speed, the linear way and the angular or spinning way. So how do they connect? How do we build a bridge between these two worlds? To really nail this down, let's picture an old-school vinyl record spinning on a turntable. Now imagine we've put two tiny dots on it with a marker. One is really close to the center label, and the other is way out on the very edge of the record. Now, as that record spins, both of those dots complete one full 360-degree rotation in the exact same amount of time, right? That means their angular velocity, their spin rate, is exactly the same. But look at the actual path they travel. The dot on the edge has to trace a much, much bigger circle to get back where it started. So to cover that longer distance in the same amount of time, it must be moving faster. It has a higher linear velocity. And that simple, beautiful relationship is captured perfectly in our third and final equation, v equals omega times r. Your linear speed is simply your angular, or spin speed, multiplied by how far you are from the center of the circle. This is the bridge that connects the two worlds. All right, let's put it all together. With these three simple equations, we now have a complete, powerful toolkit to analyze basically any uniform circular motion you can think of. Here it is, your complete toolkit. Number 1, the linear view, AC equals v squared r. Number 2, the rotational view, AC equals omega squared r. And number 3, the all-important bridge that connects them, v equals omega r. Depending on what information you have, the path speed or the spin speed, you've got the perfect tool for the job. And believe me, this isn't just stuff for a physics test. This toolkit is fundamental to how the world works. It's how we understand planets staying in orbit. It's what determines how fast a car can take a corner without skidding out. It's how a centrifuge works. The physics of spin is literally everywhere you look. So to leave you with one last thing to chew on, let's go back to that inward pull. Picture spinning a ball on a string over your head. That string is providing the inward centripetal force. What happens in the exact microsecond that the string snaps? Does the ball fly straight out from the center? Does it keep curving for a bit? The answer is all about the true direction of its velocity at that one final instant it was set free.